Worked example 6, series resistors. Question 1. A simple series circuit is made up of two resistors that are 50 and 80 ohms. They are connected to a 5-volt battery. Question A, sketch the diagram. B, determine the total circuit resistance. C, determine the current in the circuit. D, calculate the potential difference over each resistor. E, determine the power of each resistor. And part F, determine the energy consumed in each resistor after 1 minute of running. Alright, so we have our list of things to do, so let's get started. So we're told that it's two resistors in series, so that's going to be a straightforward circuit of a battery. So our VS, and we're told the supply voltage is 5 volts. And straight into that is two resistors. And we're told the resistor R1 is 50 ohms and resistor R2 is 80. For part B, we're asked to work out total resistance. Now, these two resistors are connected in series. So when you have one resistor after another in series, we add the resistances together. So for series, our total resistance is R1 plus R2 in this case, which is going to be 50 plus 80, which is going to become 130 ohms of resistance. Part C, we're asked to work out the supply current, and this is where we remember Ohm's law from the previous section. We've got a supply voltage of 5 volts, we've got a total resistance of 130, so V equals IR, and we need to rearrange this to I is V upon R, and substitute in our values. So in this case, I is going to become our voltage of 5 volts divided by a resistance of 130, which gives us 38.5 milliamps, or 38.5 times 10 to the minus 3 amps. Then we're asked to work out voltage over 1 and 2. So there's, again, multiple ways to do this, as always. You could use the voltage divider rule. So the voltage will drop proportionally over each resistor based on the value of the resistance. So just quickly, if we take the total resistance and then we have each value of resistor, so let's say R1, and multiply it by the supply voltage, then we'll get the voltage over that resistance based on the proportionality here. So if we do 50 over our total resistance of 130 times 5, we end up getting 1.92 volts. And then we could do the same if we do 80 over 130. Again, we're doing proportionality here, so it's based on proportions, or ratio if you like. 80 over 130 times 5, we will get 3.08 volts. This is a completely legitimate way to do it, and you would get full marks for that. Another way we could have done that is we could have worked out the the voltage over R1, and then subtracted that from the supply voltage to get the resistance over R2. So for example, we could have done our V2 is VS minus V1, which would be 5 minus 1.92, which again gives us 3.08 volts. And so you can see those two answers actually match up, and that's perfectly fine. And lastly, the way I've done it in the book here is you can just use V equals IR. So we could say, well, V1 equals the current flowing through resistor 1, which in this case is the supply current, because as you know, in a series circuit, the current from the battery goes through all the elements and returns. So whatever current is the supply current is the current flowing through R1, and is going to be the current flowing through R2 in this case. So we can just use V equals IR and say that voltage 1 IS R1, our supply current here is 38.5 times 10 to the minus 3, multiplied by the value of the resistor R1, which was 50. And when we do that, we end up getting 1.92 volts. And the same for V2, we can say that V2 is IS times R2, which is 38.5 times 10 to the minus 3, multiplied by 80, and that gives us 3.08 volts. So there's multiple ways we can do it. You can do it this way, which is absolutely perfectly legitimate, or you can do it the way I've done in the book as well, which is just using Ohm's law and calculating the voltage drop via that. Part E, we'll just do it over here. Part E is asking us for the power of P1, P2. So for that, again, there's multiple ways. P equals IV. So the power of resistor 1 is going to be the current flowing through resistor 1 times by the voltage drop over resistor 1. So in this case, we have our current flowing through it, 38.5 times 10 to the minus 3, multiplied by the voltage across resistor 1, which we've just calculated, is 1.92. And when we do that, we get 79.3 milliwatts. For P2, we have IS times V2, which in this case, same current because they're in series, times our voltage over R2, which is 3.08, and that gives us 119 milliwatts of power. And then finally, for part F here, we're asked to calculate what was the energy consumed or converted by each resistor after 1 minute of operation. Well, E1 is going to be determined by the power of resistor 1, which we've got here, multiplied by how long that resistor has been running for. So we've got 79.3 times 10 to the minus 3, multiplied by a time of 60 seconds, and that gives us a total power of total energy of 4.76 joules. E2 is going to be the power of number 2 here, so it's 119 times 10 to the minus 3, again multiplied by 60, and that is going to give us 7.14 joules. Just a little note in the book, when I've written it, I've written the current as 0.0793 and 0.119. So those are just different ways of writing the same thing. That is effectively that, and that is that, that is that. It's the same thing, just written in a slightly different format. Question 2. A simple series circuit is made up of 2 resistors. So a quick sketch here. R1 and R2 have potential differences of 8 volts and 4 volts respectively. Okay, so we've got R1 here, we've got R2, and we're told that R1 is 8 volts and R2 is 4 volts. Just a little comment on the wording there. When you hear the word respectively, so have potential differences of 8 volts and 4 volts respectively, that basically just means in the order that you've heard them there. So when you're told R1 and R2 have voltages of 8 and 4 respectively, that always means that the first number applies to the first thing and the second thing applies to the second thing. So 8 volts over R1, 4 volts over R2. Okay, so those are our voltage drops. We're also told that it has a supply current of 1.2 amps, so our IS is 1.2 amps. And we're asked to determine each of the following: the battery EMF, resistance of R1 for part B, resistance of R2 for part C, and powers P1 and P2 for part D. So from the information in the question, we have to figure all these out. So our supply voltage here is going to be equal to the total voltage drop over each resistor added together. So when you've got resistors in series like this, the EMF, or the supply voltage, is equal to the voltage drop over each individual resistor in series. Okay, so let's start that by saying that in series, our supply voltage is equal to V1 plus V2. Now, the more complicated version of that would be to say that in a closed loop, the sum of EMFs, or the sum of voltage drops, I should say, so the sum of potential differences in a closed loop will equal the sum of voltage supplies, so sum of EMF, which is Kirchhoff's voltage law, one of them in a closed loop. So effectively, we can think of the closed loop as the circuit here. V1 is 8 volts, and draw that, plus our V2 of 4 volts, so we get a total voltage drop of 12 volts, and that equals our supply voltage. We're then asked to work out the resistance of R1 and R2. Well, in this case, because it's a series circuit, and we're given the supply current, we know the current now flowing through both resistors, each resistor I should say. We've got V1, we've got effectively I1 here. R1 is going to be V over I, 1 and 1, or supply in this case because it's series. So V1 was 8 volts over our supply current of 1.2 amps. And that gives us 6.67. Part C, we're asked to work out R2, which again is going to be V2 over IS. So the same as before effectively, except this time it's 4 volts divided by the 1.2, and that gives us 3.33 ohms. For part D, we're asked to work out P1 and P2. Power 1, in this case, is going to be IV. IS times V1 is going to be our 1.2 amps multiplied by V1 of 8, which is going to give us 9.6 watts. And then power 2 is going to be equal to IS times V2. So that's going to give us 1.2 times 4, and that also gives us 4.8 watts. Then on the following page, which I just totally didn't forget about, is question E, which then asks us to show through calculation that the total power of the circuit equals P1 plus P2. So through calculation, total power equals P1 plus P2. So part E here is asking us to prove that the total power is equal to P1 plus P2. Now this kind of question often throws students, and because the reason being is they're like, well, what does that actually mean? And it's actually a lot simpler than one might think at first. And it's just to show, it's just for you to show through calculation that the total power that you can calculate with P equals I S Vs is going to be equal to power 1, which you can calculate individually, plus power 2, again, which you calculate individually. And we've already done power 1 and power 2, we did it right here. So really all that's left to do is to calculate our total power with this equation, which is going to be our supply current of 1.2 times our supply voltage this time of 12, which equals 14.4 watts. To show that the total power equals the individual powers added together, well, we can just do that by saying, well, P1 is 9.6 plus P2, which is 4.8. And when you do that, you, oddly enough, get 14.4 watts. So we can show that 14.4 equals 14.4 watts. Therefore, the power total does in fact equal P1 plus P2. Very simple calculation, but effectively that's what it's wanting to demonstrate, that the individual powers, when added, give you 14.4, and that the total power, when calculated, gives you 14.4, and obviously those two are the same number, therefore the PT does in fact equal P1 plus P2. And then part F, energy consumed by R1 after 60 seconds. So energy of R1 at 60 seconds asks us to work out energy 1 at 60 seconds. So E1 is power 1 times time, which in this case power 1 was 9.6 times 1 minute of running, which is 60, and that gives us a total energy consumed of 576 joules of energy. And then part G, the energy consumed by the circuit, so energy total, consumed after 2 minutes of running. So let's do part E here. Finally, in part G, asking us for the total energy consumed, ES, or total energy supplied, which is going to be the power total of the circuit multiplied by the time it's running, which in this case is 14.4 watts for the total power, multiplied by our time running 2 minutes times 60. and that gives us 1,728 joules of energy, or 1.73 kilojoules. Question 3. A 3 resistor series circuit this time is connected to a 24 volt battery. After 10 minutes of running, it has consumed 10 kilojoules of energy. Determine the following: A, supply current, B, total resistance of the circuit, and if all 3 resistors have the same value of resistance, determine the resistance of each resistor. Okay. And then finally, part D, the voltage drop over each resistor. So the first thing we're going to do is just quickly sketch out a little circuit here just to keep ourselves right, and doesn't have to be overly pretty. What we're told that we've got a 24 volt battery and that it's been running for 10 minutes and the total energy consumed after 10 minutes is 10 kilojoules at 10 minutes run. Right, so this is where we get into some of the first multi-step equations, because now it's no longer a case of we can write I equals something and substitute in values and get that. Alright, so now we have to look at, well, what information do we have and what steps can we take to get to the information we want? Well, we've got E, and the first thing I would say is, what to think of is, right, well, I've got E and I know E equals P times T. So that's one equation I've got. What else do I have? Well, I've got voltage and I know V equals IR. I know P equals IV. So is there a way that I can use some of this information or some of the information available to end up getting to I? And the answer is yes, because actually we do have voltage, we're looking for this, but we don't have P. But we do have energy and we've got time, and we can find out P. So if we can find this P, we can substitute that into there, and that'll let us get to our I. So it's a case of sort of process of deduction. Now, once you've done it for a long enough time and you've done enough of them, eventually this becomes second nature and you just know, well, I need to find that and I need to find that to get this. Initially, my advice, and it's the advice I always give to people, is write out the equations you know that involve the information you've got. There'll be a certain amount of practice you have to put in so you know which equations are going to apply to the questions you're working with. So in this case, I'm going to look for P first of all. So power is energy over time. We're told 10,000 joules divided by my time of 10 minutes. So 10 minutes is 10 times 60 seconds per minute. That gives us a total power of 16.67 watts. We need to take this another step further and actually calculate our current based on that. I is going to be power divided by voltage, which we do have, and our power is 16.67, which we just got, divided by our voltage of 24 volts from the question earlier. And in this case, our current is 695 milliamps. Part B asks us to work out the total resistance of the circuit. So our total resistance, RT, is what we're looking for. Our resistance is V over I. So in this case, RT is going to be the supply voltage of 24 divided by the supply current of 695 times 10 to the minus 3 is equal to 34.5 ohms. Part C is the tricky one, where we're told in the question, if all 3 resistors have the same value of resistance, determine the resistance of each resistor. So this is where you have to think backwards a little bit here, or work backwards I should say. Don't want to think backwards, we want to work backwards and say, well, we've got the total resistance, 34.5, and we know it's a series circuit because we're told that resistance total is equal to R1 plus R2 plus R3, and we know that all 3 resistors have the same value, then that means we could say, well, let's just call it R plus R plus R. Well, R plus R plus R is going to be 3R, and we know the total resistance is 34.5. So what we can do is we can say, well, R is just going to be 1/3 of that, which in this case equals 11.5 ohms. Finally, how do we work out the voltage over each resistor? We've got a slightly simpler question than it may first appear. Since the resistance of each resistor is the same and they're in series, that means the voltage over each resistor will be the same. So there's two ways we can do this. We could just take 24 and divide it by 3, and that will give us the voltage drop over each. Or we can use Ohm's law and say, well, V equals IR, and my current is 695 times 10 to the minus 3 times R, and the value of one resistor is 11.5, and that is going to give us a voltage of 7.999 recurring, or 8 volts. And if you look, 24 divided by 3 is also 8 volts. So either way, absolutely fine, as long as you understand sort of why that's the case, because each resistor is the same. And you can do it this way as well, which is just a more by the numbers approach, if you like, using Ohm's law, to make sure that you're explaining to the examiner so they know that you know V1 equals V2 equals V3 equals 8 volts. And that way there's no misunderstandings, and you definitely get the marks for that. Alright, question 4 from the worked example here. The total voltage drop over 3 resistors connecting in series is 24 volts, so Vs is 24 volts. And in the picture of the question, we're given 3 values of resistance, 22, 76 and 50. So just go ahead and draw a little representation of that to work with here. And we're told the total voltage drop is 24. And in part A, we're asked to determine the voltage drop over R1. Give your answer to 2 decimal places. Give answer to 2 decimal places. So, as with most questions, there are actually multiple ways we can do this. We can do the voltage ratio method. Because the resistors are in series, the voltage will split based on the resistance, and I'll do it that way. And then the other method we could apply is we could work out the total resistance by adding them, and then work out the current, and then work out the voltage drop by doing our resistance, using resistance and current to work out our voltage drop here. So let's do it with both methods. The first method uses the ratio, so our formula would look a bit like this. V1 is going to be equal to R1 over RT times the supply voltage. And that is basically just to say, in a fancy way of add these 3 together to get total resistance, divide the first one by that to get the ratio, and then multiply by the supply voltage or the total voltage drop to figure out how much of the voltage drops over that resistor. So let's do that. So that becomes 22 over 22 plus 76 plus 50 multiplied by total voltage drop of 24 volts, and that ends up giving us 3.57 volts. The alternative method is that we add these 3 together. RT equals 22 plus 76 plus 50, which is 148 ohms. And then we can work out our supply current with V over R, T, which is 24 over 148, which becomes 162 milliamps. And so with our supply current and our R1 here, we can then say that V1 equals IS times R1, which is 162 times 10 to the minus 3 multiplied by R1 of 22 equals 3.57 volts. So 2 ways to get the same answer. Either way is perfectly acceptable. This is probably the quicker and easier way of doing it. It's just basically it's one equation, one substitution, one answer, one step, if you like. Whereas this one involves total resistance, getting your current, and then working out your voltage based on that. But as I say, either way would get you the marks for that question.